online now, and I will present my slide again. This is the slide with 13 eigenvalues and eigenfactors problem. What is eigenvalues problem? Let we have given, and we want to find factor x, where if the factors fulfill this equation. Okay. And there are two unknown object will be determined. The first is factor x, and the second is the value of lambda. So we if we have this condition, ax is equal to lambda x, so this problem is called as eigenvalues problem. In engineering problem, this condition is important. There are several conditions fulfill this condition. So we must know how to find factor x and value of lambda. And number lambda is called an eigenvalue of A. Yeah, so we are calculating x and lambda. And how to calculate or determine eigenvalue and eigenfactors. Oh, sorry, I will tell you eigen. Eigen is a word from Germany. It means characteristic, character of fact of matrix. Eigen is not a name of someone, a person, but eigen is a word from Germany. Okay, we go back to our problem. How to determine eigenvalue and eigenvectors? The first step is we must determine eigenvalue. After that, we determine eigenvectors. So there are two steps. The first determine eigenvalue, and the second determine the eigenvector. And how to find eigenvalue? Eigenvalue can be determined from this condition. So this is a condition. We can elaborate, or we can I mean show why this condition happened, but I think it's to takes time. So we take it for granted, yeah. So just uh, take it as a formula. This is the formula to determine or to find the value of eigenvalue. Then the value of the value of lambda. So this is the formula to get it. And for eigenvector, we can use this formula. This is the the formula to find eigenvectors, and there are this one formula to find the value of lambda. This is vectors, and lambda is value. And what is this? This is identity matrix. Identity matrix, and depend on our matrix, the size of A, 3 times 3. So the identity matrix should be 3 times 3 also. If A is 4 times 4, so I is also okay. The eigenvector can be determined after eigenvalue. So we must find eigenvalue first. After that, we we can find eigenvectors. Why? Because we in this equation, eigenvalue substitute from the value from here, from this equation. So we must get eigenvalue first. After that, we can find eigenvectors. Okay, before we show you how to find eigenvalue and eigenvectors, we also tell you several properties of eigenvalues. This is the properties of eigenvalues. The first one is if a triangle matrices, then the eigenvalues of A is the elements located on the main diagonal. So this is some this is useful to find eigenvalues easily if A triangle matrices. Yeah. Triangle can be upper triangle or lower triangle. So for example, this one, yeah, this one I will pick up the tip of my pen. So this is uh, can be maybe 1, 2, 3, minus 1, 1, 0, 0, 0, minus 4. This is uh, we call it upper triangular upper triangle. So the other triangle, for example, minus 1, 0, 0, 1, 2, 0, 2, 3, 4. This is also a triangle. Yeah. So and the eigenvalues for this matrix can be get directly from the main diagonal. So this is the eigenvalue of these matrices. Okay, so this is uh, properties property number one for eigenvalue. Okay, let's we continue. Positive integer, positive k is a positive integer, and x and lambda is an eigenvalue and eigenvectors of A. Then x and lambda power of key is an eigenvalues and eigenvectors of A power of key. So we don't need calculate eigenvalues and eigenvectors of A power of key. Just just taking the eigenvectors and eigenvalues of A from A. So we claim, yeah, we claim the eigenvectors is the same with eigenvectors of A. and eigenvalue is power of k from eigenvalues of A. So this one, A have eigenvalue lambda and x, eigenvector of x. So A power of k will have eigenvalue lambda power of k, and the eigenvector is still x. Yeah. So it's make us know uh, eigenvalue and eigenvectors of A power of k easily. If A invertible, so invertible means that A power of minus one exists, yeah, exists. We can find the inverse of A if and only if lambda is equal 0 is not eigenvalue of A. So this will be accessed if their eigenvalue is not equal to 0. Yeah. Okay, let's we uh, continue with the exercise. As we mentioned before, we must know eigenvalue first. We must know eigenvalue first, and then we determine the eigenvectors of A. Vector of A. Okay, let's we do. Yeah, let's we show how to find the the eigenvalues of A and eigenvectors of A. The to find eigenvalue, I write the formula to get the eigenvalue. Determine 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 determinant determinant A minus lambda identity is equal to 0. So we try to make A minus lambda E. A minus lambda E will be A itself is A 1 minus 0 what is 0 uh, 1 0 uh, 0 uh, 15 and minus 2. Yeah. This is the A. Okay, A minus lambda multiplied by identity 1 0 0 1 0 0 0 1, and we multiply lambda to every element in this matrix, but we get only in the main diagonal because the other is 0, 1, 7, minus 1, 0, 1, 0, 0, 15, and minus 2, and then minus lambda 0, 0, 0, lambda 0, 0, 0, lambda. So we subtract first uh, first matrix from second matrix. We have 1 minus lambda 7 minus 1. This is 0. What else? This is 1 minus lambda 0, 0, 15 minus 2 minus lambda. Okay, we get the determinant. We get A minus lambda identity. So we calculate the determinant of 1 minus lambda 7 minus 1 1 minus lambda, 0, 0, 15, minus 2 minus lambda. Okay. We know that the determinant can be get by using what we call expansion, column or expansion of row by minor cofactors. So we use the expansion uh, first column. Yeah, we use uh, expansion expansion first column, column one. Yeah, expansion column one, and uh, the determinant is A11. I hope you still remember what is the formula of determinant. Expansion column one means that A11 multiplied by C11 plus the other elements is A21, C21, and the third is A31, C31. Yeah. Uh, because this is 0, also 0, so we only have A11, C11. And what is A11? A11 is 1 minus lambda. Yeah, this is A11, A11. And then C11 is minus 1, power of 1 plus 1, 1 plus 1, and multiplied by M11, M11. And this is positive. So 1 minus lambda and multiplied by M11. M11 is deleting first row and first column. So we have this one, 1 minus lambda, 0. This is 15, and minus 2 minus lambda. And determine the determinant 2 times 2. We have that this is main diagonal and other diagonal. So we have 1 minus lambda multiplied by this one, 1 minus lambda multiplied by minus 2 minus lambda minus 0. 15 times we have 1 minus lambda and 1 minus lambda and minus 2 minus is the determinant of A minus lambda I, lambda I. So determine A minus lambda in square and the formula say that equalize we must equalize by 0. Yeah, we must uh, equalize by 0. So this is will be 0. And the eigenvalues is the solution of this equation. Yeah, solution of this equation. And the solution is solution of determinant A minus lambda I is equal to 0, R, there are three. The uh, lambda I, lambda 1 and 2 is repeated and the same value 1, and the others lambda 3 is equal to minus 2. Yeah, minus 2. So this is our eigenvalue. The eigenvalues of A are, there are lambda 1 comma 2 is equal to 1, and lambda 3 is equal minus 2. So this is the eigenvalues of eigenvalues of apa, of A, ya. Eigenvalues of A. And then what is the eigenvectors of A? Yeah, eigenvectors of A can be get from the eigenvalue of A. So uh, we associate the eigenvectors from eigenvalues. So we must uh, we must uh, find one by one. Uh, for lambda 1 comma 2 is equal to 1. Yeah, we substitute uh, this uh, this lambda uh, to this equation. Yeah, we substitute the value of lambda to this equation. So we have that uh, a we have that a minus lambda is equal to 1. So a minus I multiplied by factor again factor x is equal to 0 factors. So we have from here we have one. Sorry, I still don't remember. 1 7 minus 1 0 1 0 0 15 15 minus 12 subtract by identity 1 0 0 0 1 0 0 0 1, and this is will be multiplied by x is x1 x2 and x3, and then is equal to 0 0 0. Yeah. Okay, we subtract them. We get that 0, yeah, 1 minus 1 is 0, 7 minus 1, and this is 0 0, 1 minus 1 is also 0, this is 0, and the rest, this is minus 2, yeah, minus 2. Minus 2, this is 15, and minus 2, minus 1, minus 3. And multiply by x1, x2, and x3. And is equal to 0, 0, 0. And we know this is a linear equation system. This is the homogeneous linear equation system. Sistem persamaan linear homogen. This is homogeneous linear equation system. So we know from the previous chapter how to find this solution of homogeneous linear equation system by using operation row elementary. Row operation matrix, yeah. So we make this one 0 7 minus 1 0 0 0 0 0 0 15 minus 3 0. Yeah, uh, we we take the left side, the right side to the matrix. Yeah, become augmented matrix. So from now we want to apply a row operation matrix. We can switch row 2 with row 3 like this. Row 2 uh, switch with row 3. We have that 0 7 minus 1 0 and 0 15 minus 3 0 0 0 0 because we want to make 0 rows in the bottom, and then we want to find a leading one. In this case we can use this operation, row 2 uh, subtract by 2 row 1, because 15 minus 14 will be 1. Yeah, so we have the operation 0 7 minus 1 0 0. Yeah, 15 minus 2 times 7 will be 1. Yeah, will be 1. Then minus 3 minus 3 minus 3 minus 2 minus 1, so we have minus 1. Yeah, so this is minus 1 and 0 0 0 0 0. Okay, after that we can switch again row 1 switch by row 2. Yeah. We have that 0 1 minus 1 0 0 7 minus 1 0 0 0 0 0. Okay, after this one we want to make 7 become 1, yeah, because you want to make a row at reduce row echelon matrix. So this is should be 0. We do the operation row 2 minus 7 row 1. We have that 0 1 minus 1 0. This is will be 0, and this is will be 0, and this is must be minus 7 times minus 1 7, add to minus 1, so we will have 6 0 0 0 0 0. Okay, still continue. We divide row 2 by 6, 1 over 6 row 2. We have that 0 1 minus 1 0 0 1 0 0 1 0 0 0 0 0. Okay, and the last step is we want to make minus 1 become 0, so we add a row 1 by row 2. We have the final result is 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay. Uh, from the last the last we stop here because we already have reduced row echelon matrix. So we go back to the system. From the last we have that x2 is equal to 0. Yeah, because this is x2 is equal to 0. And from the second row, we have x3. X3 is equal to 0. But we don't know any clue to find x1. Yeah, x1. So x1 will be anything. So we can write x1 is equal to t, yeah, for or any symbol, yeah. We can use any symbol. Okay, I make it more uh, uh, in the corner. I make it here, yeah, here. So x2 is equal to 0, x1, x3 is equal to 0, x1 is equal to t. And then we make it in order, x1, x2, and x3. Uh, so we have t 0, 0. And extract t from these vectors, we have that t times by 1, 0, 0. Yeah. Now we get the eigenvectors. Eigenvector is this basis. Yeah, this basis. This is eigenvectors. So the eigenvectors, the eigen factors of A is x, yeah, factor x, but with indication, by indication, lambda 1 and comma 2 is equal to 1, 0, 0. This is our eigenvectors uh, based on this lambda. Yeah, this is how to find eigenvectors based on this lambda. Okay, now what is the other eigenvectors? Because we have two eigenvalues, so we must find the second one. Second one, it means uh, uh, we must find for lambda 3 is equal to -2, equal to -2. Uh, yeah, to make it shorter, I don't write like this. I jump into this one. Yeah, I jump into this one. It means that I use this equation, and replace lambda by -2 from this one. Yeah, from this one, replace lambda by -2. Lambda by -2. So I jump into this equation to make it shorter. So I replace lambda by -2. 1 minus minus 2 is 3. 3, 3, 3, 7, and minus 1. And then 0, 1 minus minus 2 is also 3. So 0, 0, 3, 0. And the last row 0, 15 and minus and 0. Yeah, minus 2 minus minus 2 is 0. So this is 0, 15 and 0, and multiplied by x1, x2 and x3, and this is equal to 0, 0, 0. So I make it shorter without calculate, subtract. I jump into substitute lambda by minus 2. Yeah. So I get directly this equation. So this is the equation after substitute lambda 3 is equal to minus 2. We have also this homogeneous linear equation system, and then we make augmented matrix 3, 7, minus 1, 0, 0, 3, 0, 0, 0, 15, 0, 0. So we do again this row operation matrix and divide row 1 by 3, 1 over 3, row 1, also 1 over 3, row 2. So we have, we have 1 here, 1, 7 over 3, minus a third, 0, 0, 1, 0, 0. Okay. We also might be of, let's we uh, do the operation like this. And then row 3 minus 15 row 2 to make row 3 0. We have the result is 1 7 over 3 minus 1 over 3 0 0 1 0 0. This is 0 0 0 0. So the third row is 0. And then we make 7 minus 3 7 over 3 is 0 by using row 2, row 1 minus 7 over 3, row 2. We have that 0, 0, 0, 0, 0, 1, 0, 0. This is will be 1, 0. This is minus over 3, 0, like this. Yeah. Okay, stop, because we have already reduced row echelon matrix. And then we go back to the system, translate it, become our system again. So we have x1 minus 1 over 3 x3 is equal to 0. And from the second, we have x2 is equal to 0. And it means that finally we only have one equation, and from this equation we can suppose or let x3 by t or by s, anything we like, maybe by t. So uh, by letting this one, we have that x1 will be 1 over 3 t, because x1 is equal to 1 over 3 x3. Okay, let's we make it in order again. X1, X2, and X3. From our result, we have that X1 is 1 over 3t, X2 is 0, X3 is t. And extract t from the factors. We have 1 over 3, 0, and 1. And again, this is our eigenvectors. Yeah, eigenvectors. So the eigenvectors of A associate or related uh, related to lambda 3 is equal to minus 2 is, yeah, because only one factors. uh, we have that x lambda 3 is 1 over 3, 0, and 1. Okay, so this is our eigenvectors, and I will make a summary for this problem. So we have A is 1, 7, minus 1, 0, 0, 1, sorry, 0, yeah, 0, 1, 0, 0, 15, and minus 2. This matrix have the eigenvectors, the eigenvalues of are lambda 1 comma 2 is equal to 1, and lambda 3 is equal to minus 2. And from this matrix, we have the factors of A of A uh, related to lambda 1 comma 2 and lambda 3 is equal to minus 2 respectively are lam x x lambda 1 comma 2 is equal to 100, and x lambda 3 is equal to 1 over 301. Yeah, this is the summary of our problem. Yeah, so this is the eigenvalues, and this is the this is eigenvalue, yeah, eigenvalue, and this is eigenvectors, and this is also eigenvectors, and this is the summary. This is the solution of this example or this exercise. Okay, let's we continue. We still have some problem to solve. Uh, okay, let's we continue. Are you still here?
Yes.
Yeah, okay. Uh, uh, wait a minute. Okay. Do you still do you still look at the slide, and the slide is moving to another slide still?
It's not moving.
Okay. I'm afraid I
Oh, no,
just
it's moving.
yeah. Okay. But thank you. Yeah. Now exercise 7.2. We have this matrix A, and as we know from the property that this is triangle matrix. We know this matrix is triangle matrix because uh, in the below of main diagonal, the elements in the below of main diagonal are zero. So this is triangle matrix, and from the property, uh, the previous property say that the main diagonal is are the eigenvalues of A. So we are not necessarily to calculate. Yeah, uh, we don't need uh, necessarily to calculate. We can say that from this exercise directly. The eigenvalue of A is lambda 1 is minus 1, lambda 2 is 1, and lambda 3 is 3. Yeah, without calculate. From this exercise, item A, the eigenvalues are solved. Eigenvalues are solved, and we can calculate the next problem is find eigenvectors. Okay, so a solution A, the eigenvalues, the eigen values of A, uh, lambda 1 is equal minus 1, lambda 2 is equal to 2, and lambda 3 is equal to 3 from the properties, yeah, from the property of eigenvalues of A. Eigenvalues of A, yeah, without calculate. So next, we must calculate the eigenvectors. Yeah, eigenvectors. The eigenvectors is one by one, as I told you before. For lambda 1 is equal to minus 1. Substitute this value to the equation. The equation is A minus lambda I multiplied by x is equal to 0 vectors. So substitute minus 1 here, minus 1 in here. So we have this is plus, yeah, plus I. Plus I means that in the this matrix in the main diagonal will be added by 1. So we have that the equation will be 0 here, minus 1 plus 1, 2, 2, 0, 0, this is 2, and minus 5, minus 5, minus 5, then 0, 0, this is 4, yeah, 3 times 1, and multiplied by x1, x2, x3, x3, and this is 0, 0, 0. So again, we have the problem to solve homogeneous linear equation system like this. And we have that 0, 2, 0, 0, 0, 2, minus 5, 0, 0, 0, 4, 0, and divide by 2, 1 over 2, R1, 1 over 2, R3, R2, yeah, R2, we have that 0, 0, 1, 0, 0, 1 minus 5 over 2, 0, 0, 0. I think we can divide by 4 directly, 0, 1, 0, like this. And subtract R2 by R1, row 1. We have this is 0, 1, 0, 0, 0, 0. This is minus 5 over 2, 0, 0, 0, 1, 0. Okay. So we can use this operation from R3, 5, sorry, R2, add by plus 5 over 2 R3 to make row 1, row 2 is 0. 1, 0, 1, 0, 0, 0, 0, 0, 0, and 0, 0, 1, 0. Yeah, because we add 5 over 2 to minus 5 over 2. And switch R2 by R3. R3, we have 1, 0, 1, 0, 0, 0, 0, 1, 0, and this is zeros, 0 row. Okay, let's interpret this matrix. We stop here because this is already a row echelon matrix. So we interpret it to the system. We have x2 from the first row. We have x2 is equal to 0. And the second, we have x3 is equal to 0. And we don't know about x1. So we letting x1 by t. And t is any number. So we get that x1, x2, and x3 will be t00, and extract t, we have 100, and we get this is the eigenvectors, yeah. Eigenvectors related to lambda 1 is equal to 100. Okay, this is still in the first eigenvectors, and we must calculate for the second and for the third, yeah, for the third. Okay, let's we do uh, quicker for lambda 3 is equal to 2. Yeah, minus 1, minus 1. Yeah, okay, minus 1, minus 1 plus 1. Okay. For 2 means that we replace what is we replace, yeah, we replace lambda by 2, yeah, by 2, and it means that main diagonal must be subtract by 2. Main diagonal of A must be subtract by 2. Okay, let's redo. We subtract main diagonal of A by 2, yeah. So we have that this one, for example, minus 1 minus 2 will be minus 3. This will be 0, and this is will be 1. Yeah. So we have minus 3, 2, 0, 0, 0, 0, 0, and minus 5, minus 5, minus 5, and this is 0, 0, 1. Yeah, divide by multiplied by x1, x2, and x3. Okay, so we have another homogeneous linear equation system. Here we have that minus 3, 2, 0, 0, 0, 0, minus 5, 0. So it's a routine, yeah, routine 0 like this. Okay, so we make it 0 row 2 plus 5 row 3, and we divide row 1 by minus over 3 row 1. So we have 1 minus 2 over 3, 0, 0, 0, 0, 0, 0, and 0, 0, 1, 0. And switch R2 by R3. Okay, we have final result 1 minus 2 over 3, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. And it means that we have x1 minus 2 over 3, x2 is equal to 0, and x3 is equal to 0. And by from the this first equation, we are letting x2 by t, so we have x1 is equal to 2 over 3 t. Okay, then rearrange the vectors x1, x2, and x3. We have that root 2 over 3 t, x2 t, that x3 is 0. So we have that 2 over 3, 0, 0, 1, 0. And again, we have, this is the eigenvectors, x lambda 2, oh, sorry, this is lambda 2. Lambda 2 is equal to, eigenvector is 2 over 3, 1, 0. Okay, so we can put lambda for lambda 3 here. 3, it means that again we subtract main diagonal by 3. We have that this is will be minus 4. 2, 0. This is will be 0, minus 1, minus 5. This is will be 0, 0, 0. And then x1, x2, and x3. And this is equal to 0, 0, 0. Okay, then yeah, so routine, yeah. Because we uh, we are repeating such same procedure. So this is divide by what we, okay, let we do this one. Minus 4, 2, 0, 0, 0, minus 1, minus 5, 0, 0, 0, 0, 0. Then multiply R2 by minus 1. R2, we have that 0, 1, 5, 0, 0, 0, 0, 0, minus 4, 2, 0, 0. And then uh, we want to this value number uh, value of 2 becomes 0. So we can do R1 minus 2 R2. So we have that 0, 0, 0, 0. This is 0, 1, 5, 0. This is will be minus 4, 0 here. This is minus 10, yeah, and 0. And divide R1 by, so I put here, divide R1 by minus 4 R1, we have that 1, 0, minus 4, minus, uh, this is will be 5 over 2, 0, 0, 1, 5, 0, 0, 0, 0, 0. Okay, this one. Okay, we already have row echelon, reduced row echelon matrix. So we interpret the system again. We have that x1 plus 5 over 2 x3. X3 is equal to 0. X2 plus 5 x3 is equal to 0. X2 is not identified, so X2 is uh, sorry, X3, yeah, X3 can be letting uh, by T, and X2 will be minus 5T, and X1 will be minus 5 over 2 T. Yeah, so uh, we have that by ordering, make in order x1, x2, and x3 will be here minus 5 over 2t, minus 5t, and 1, and t, sorry, t, and extra t, we have that minus 5 over 2, minus 5, 1, and then we have the eigenvectors of lambda 3 associated with lambda 3 is minus 5 over 2, minus 5, and 1. Minus 5 and 1. Okay, let's we summary, yeah. Let's we summary. Before we summary, we can go to B first, maybe. B. D is determine the eigenvalues and eigenvectors of A square. A square. We from the properties, properties of eigenvalues of eigen problem of A, we have that uh, of for a square, the eigenvalue is square of the eigenvalues of A. Yeah, we can square minus 1. This is 1, and the eigenvalues, the second eigenvalues is 2 square is 4, and the third eigenvalue is uh, 3 square. We have 9. So uh, we have that factor eigens is same with the factor eigen of A. Uh, uh, x x lambda 2, and this is x lambda 3, yeah, for A square. Yeah, we have like here, and this is the same with the eigenvector of A. Okay, we make it. This is 1 0 0, and this is 2/3. Uh, 2/3 and this is minus 5/2 5 1. Yeah. So the summary for this problem, summary for this problem of exercise 7.2. We have A is -1 to 0, 0 to what we have 0 to -5, -5, minus -5, and this is 0 0 3. Yeah, and the problem A, we have lambda 1 is -1, lambda 2 is 2, and lambda 3 is 3. And the eigenvectors of these eigenvalues is uh, uh, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, and the eigenvectors of lambda 2 is 1 over 2/3, 2/3, 1, 0, and the eigenvectors of lambda 3 is -5/2, -5, and 1. Yeah, this is the eigenvectors of A. Uh, uh, for B, eigenvectors of A square, we have that lambda 1 is 1, yeah, -1 square. Lambda 2 is 4, 2 square. Lambda 3 is 9, 3 square. And we have the same factor eigen is 1, 0, 0, and x lambda 2 is 2/3, 1, 0, and x lambda 3 is x lambda 3 is uh, x lambda 3 is -5/2, -5, and 1. Okay, this one is the summary of exercise 7/2. Okay, wait, sorry, I made. Okay, let's we take a break for a moment because so exhausted for me. I hope you still to follow me. And until now, uh, we are presenting the technique or the calculating of eigenvalues and eigenvectors. Okay, I make a summary until now. This is the equation to find the eigenvalue of matrix A, and this is the equation to find the eigenvectors of matrix A. We substitute eigenvalues from the previous. So this is the properties, some properties of eigenvalues. We get the eigenvalues of triangle matrix directly uh, from the main diagonal. And this is the properties of for eigenvalues and eigenvectors of a power of t can be find from eigenvalue and eigenvectors of a. This is the properties of a can be invertible if and only if the eigenvalue of a is not equal to 0. And from exercise 7.1, we have eigenvalues only two. Uh, Lambda 1 comma 2 is equal to 1, and lambda 3 is equal to minus 2. And for lambda 1 minus comma 2 is equal to 1, we have the eigenvectors is 1, 0, 0. And for lambda 3 is equal to minus 1, we have the eigenvectors is 1 over 3, 0, and 1. And this is the summary for the exercise 7.1. And this is the exercise 7.2. We use the property of eigenvalues as we mentioned before. So the eigenvalue is the main diagonal minus 1. Next, we will determine the eigenvectors for each eigenvalues. This is eigenvectors for lambda 1. We have 1, 0, 0. And this is the eigenvectors of lambda 2. We have we have 2 over 3, 1, 0. And this is the eigenvectors of lambda 3. We have minus 5 over 2, minus 5, and 1. So for number P, we can get a square easily, just power by 2 for each eigenvalues. So we have minus 1 power of 2 become 1, 2 power 2 become 4, and 3 power of 2 become 9. So and the eigenvectors copy the eigenvectors of A. So we don't need to calculate anymore. Uh, okay, so this is the summary of exercise 7.2. We are given a matrix A like this, and the eigenvalues is easily can be found by from main diagonal. So the eigenvectors should be calculate one by one, and we have these eigenvectors. And this is the eigenvalues for a square. Square the each of eigenvalues of a, we have square by 2. Yeah, we have 1, 4, and 9. And the eigenvectors of a square can be found from the eigenvectors of a. Just copy the eigenvectors of a. This is the eigenvectors of a square. Okay, that's all until now. So after we summarize the the problem until now, let's we continue to the next concept. Uh, we we have the diagonalization problem. Yeah, diagonalization problem. Okay. What is diagonalization problem? Suppose or let we have the eigenvectors of A. We have n independent eigenvectors of A, and namely P1, P2, and P P1, P2, and Pn. P1, sorry, P1, P2, and Pn, like this. We have an independent eigenvectors of A. Then uh, we make a matrix P. Yeah, make a matrix P that's have P1, P2, and Pn to Pn as their columns. So we put the eigenvectors become columns of P, columns of P, yeah, column of P. So uh, we make this the multiplication of this matrix P inverse of P multiply by A multiply by we will get that this multiplication of matrix become a diagonal matrix. So the problem of diagonal, we get that P P inverse A times by P is equal to D, and where P comes from eigenvectors from the eigen values of A. Yeah. So this is related to our previous problem, finding the eigenvectors and eigenvalues. This is the diagonalization. And why we need this equation? Why we need this condition? This condition can be used to calculate this, yeah, to calculate this, yeah. if we have if we have P I inverse A, P is equal to D, so we will have that A is equal to P inverse D P, and then uh, we will have that A power of key for any key will be P inverse D key P. Yeah. So it's useful to calculate A power of any number. Yeah. So you can imagine that if we need to calculate A power of 100, so normally we must calculate A times A 2 times A 100 times. You can imagine that how how long time must it takes to calculate 100 times of A. Um, but if we have this condition, it means that we have P and we have D like this. So 100 times of A multiplication of 100 times of only 1 hour of 100, just only P D 100 times P. Just we have three matrix, not 100 matrices. Yeah. So this is the that's of diagonalization. And D square, D is lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3, yeah. Now, it means that lambda 1 power of key 0, 0, 0, lambda 2 power of key 0, 0, 0, lambda 3 power of key. So we don't need to multiply the key times, just only like this, yeah. So the diagonalization, the consequence of a diagonalization like this becomes this, yeah. This is the consequence of diagonalization. So we try to find a can be diagonalized or not, yeah, by uh, by finding the eigenvectors and the eigenvalues. The crucial one for this diagonalization is we must have uh, n independent factors. Yeah, independent factors. Yeah. If we don't have n independent factors for a n times a, so a cannot be diagonalized. So if P1, P2, Pm is less than n, yeah, less than n factors. So A cannot be diagonalized. Diagonalized. Yeah. So if less than n factors, so A cannot be diagonalized. On the other hand, if we have n independent factors, so the the uh, the vector matrix A will be uh, can be diagonalized. Okay, so we must make sure that the eigenvectors uh, must be n eigenvectors. Okay, let's we do the last exercise to make to find the diagonalization the diagonalization condition for A, and after we make sure the matrix A can be diagonalized, so we find the diagonal matrix D, uh, and then determine A power of 10. It can be anything, yeah, A power of anything, yeah, maybe 100 or 1,000 or 1 million gitu ya, can be, because the result is will be the similar, yeah, similar result. Okay, let's we do uh, um, uh, should be dirty hands, yeah, because we must work hard to find eigenvalues and eigenvectors. Okay, let's we find the eigenvalues of A. Eigenvalues of A. We have that A minus lambda I will be what we have 0, 0, 0, 0 minus 2, 0, 0 minus 2. This is 1 to 1. 1 to 1, and the third is 1 0 3 1 0 3 minus lambda I is 1 0 0 0 1 0 0 0 1, and this is will be minus lambda 0 minus 2 1 2 minus lambda 0 1 0 3 minus lambda, and then we try to find the eigenvalues is determinant of minus lambda 0 minus 2 1 2 minus lambda 0 1 0 3 minus lambda, and using second columns as the expansion, we have that 2 minus lambda minus 1 power of 2 plus 2, and the minor is the left second row and second column. We have minus lambda minus 2 and 1 and 3 minus lambda. We have that 2 minus lambda, and then minus lambda 3 minus lambda plus 2. Then we have that we rearrange minus lambda here, lambda square minus 3 lambda plus 2 plus 2. Okay, we rearrange 2 minus lambda, and this is will be my lambda minus 1 and lambda minus 2. Lambda minus 1 and lambda minus 2. Okay, lambda minus 1 and lambda minus 2. Okay, it means that we have the solution is determinant of A minus lambda I is equal to 0 will be uh, 2 minus lambda and lambda minus 1 and lambda minus 2, and we have that this is will be this will be 0, or we have that this one and this one is same. We multiply by minus 1 will be lambda minus 2 square, and lambda minus 1 is equal to 0. And we get that lambda 1 is equal to 1, and lambda 2 and 3 is equal to 2. uh, we have a repeated solution here. Okay, so we already find the eigenvalues. After we get the eigenvalues, we must calculate eigenvectors. Lambda 1 is equal to 1, we must find the eigenvectors by using this equation minus lambda I multiplied by x is equal to 0, like this, yeah. So we substitute lambda by 1. We have that Uh, it means that diagonal their diagonal lambda by -1. We have the diagonal -1, 1 and 2 like this. So we have -1, 0, -2, and 1, 1 and 0, 1, 0 and 2. Multiplied by x1, x2, and x3. This one uh, will be 0, 0, 0. And this is homogeneous linear equation system. So -1, 0, -2, 0, 1, 1, 0, 0, 1, 0, 2, 0, and switch R1 by R2, R1 by R2, we have that 1, 1, 0, 0, -1, 0, -2, 0, 1, 0, 0, 2, 0. Uh, okay, we have that this equation will be the same, row 1 and row 3. If we subtract them, we have that row 3 will be 0, yeah. We have that 1, 1, 0, 0, -1, 0, -2, 0. This is will be 0, yeah, because uh, multiplication, yeah, row 2 and row 3. And we add row 2 by row 1. We have that the result is 1, 1, 0, 0. This is will be 0, 1, -2, 0, 0, 0, 0, 0. Then we subtract row 1 by row 2 using yeah, to make it reduce row echelon matrix, yeah. 1, 0, 1, 0, 1. This is will be -2, 2, -2, 0, 0, 0, 0, 0, 0. Okay, we stop here. This is already reduced rows echelon matrix. So we have that x1 plus 2x3 is equal to 0. And this is x2 minus 2x3 is equal to 0. Let x3 is equal to t. So x2 will be to t and x1 will be minus 2t. And rearrange x1, x2, and x3, we have that this is will be minus 2t, 2t, and t. And then extract t, we have that minus 2, 2, and 1. And again, we have that the eigenvectors of lambda 1 will be minus 2, 2, and 1. Okay, then we continue to find the eigenvectors of lambda for lambda 2 and 3 is equal to 2. And as we know, it means that we must replace lambda by 2. We have here -2, 0, -2, and 1, 0, 0, 1, 0, 0, and then 1, 1, 0, 1, 1, 1, 0, This is will be x1, x2, and x3. This is 0, 0, 0, and okay, again, we have minus 2, 0, minus 2, 0, 1, 0, 0, 0, 1, 0, 1, 0. Yeah, okay. Yeah, it is so routine, yeah. Routine and okay. Let's we replace R1 by R3, R1 replaced by R3. We have that 1, 0, 1, 0, uh, and this is 1, 0, 0, 0, and this is minus 2, minus 2, 0. 0. So, uh, we have R2 minus by R1, R3 minus by 2 R1. We have that 1, 0, 0, 0, 1, 0, 1, 0. This is 0, 0, minus 1, 0, and the tip will be 0. Plus, yeah, not minus, plus. Okay. The last next is minus R3 to make it reduce row echelon matrix 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0. So we subtract R1 by R2, R1 by R2 to make it reduce row echelon matrix will be 0, 0, 1, 0, and 0, 0, 0, 0. Okay. Something uh, something wrong, yeah, something wrong. Hmm. Oh, something wrong. This is will zero, not zero, yeah. This is will be one. Ah, a big mistake. This is will be one here. Oh, huh. Ah, some, only small but affect everything. Everything from here to below. Ah, this is one, and this is should be one. Hmm. Okay. It still can be used. This is one here. One. Yeah. It can be still. Okay. This is still. Okay. Yeah. We still have here, but here we must replace by one here. One. Yeah. Because we have one here, one, and it means that this is must be one here. Okay, must be one, and this is must be one. And R3 repeat, okay. Uh, we R2 plus by 1, we must have 1 here. Replace it by 1. Uh, okay, 1. This is 1. This is 1. Uh, uh, okay, this must be 1. This is minus 1 here. 1 minus 1 here. And R1 minus R2 must be R1 minus R2 must be 0. Uh, uh, 2 minus 1 here. Okay. This is 2 and this is minus 1. And this is uh, T, okay. Yeah, still can be used, yeah. T, and this is minus 2, minus 2, 1, minus 2, 1. Okay. This, yeah. And then, we can use it. Sorry. We still can use some okay, let's we do this one. This is must be 1 here. Must be 1. Okay. Yeah. This is not uh can be used. Yeah. We must erase it totally. Some of them. I must erase one by one because Microsoft Edge don't provide the erase all. Yeah, please be patient. Okay. So this is the question, the answer. We have that this is homogeneous linear equation system minus 2, 0, minus 2, 0, 1, 0, 1, 0, 1, 0, 1, 0. Like this. And then we switch R1 by R2. We have that 1, 0, 0, 1, 0, 1, 0, minus 2, 0, minus 2, 0, 1, 0, 1, 0. So we add R2 by to R1 and R3 minus R1. We have that 1, 0, 1, 0, and the rest of row are 0 rows. Okay, now we have that we just only one equation, x1 plus x3, x1 plus x3 plus x3 is equal to 0. So let x3 is t and x1 will be minus t. And what happened with x2? X2 is also unidentified, so we must let xs by x2 by any constant, and we choose s. Yeah. S for x2. So make it in order again. X1, x2, x3. We have that this will be x1 minus t s dot n t. Then extract the the constant s or t. So we have s will be 0, 1, 0, and plus by t minus 1, 0, and 1. No, we have that new situation where for uh, lambda 2 and 3 repeat is equal to 2. We have that the eigenvectors, the eigen factors, not one but two. Yeah, the eigenvectors are x lambda 2 and 3 uh, is uh, 0, no, 1, 0, 0, 1, 0, and uh, minus 1, minus 1, 0, and 1. Yeah. So even the eigenvalues is repeated, yeah, is repeated by repeated 2 times. So we still have two eigenvectors. You can look at the difference situation with the previous previous exercise. In the previous exercise, we have that eigenvectors of 1, comma 2 repeated, uh, uh, and the eigenvectors only 1. In this case, we have that the eigenvectors is there are two eigenvectors. So we have that uh, x lambda 1, eigenvector of x lambda 1 can be replaced can be known as p1. SP1, XP1 is minus 2, 1, 1, minus 2, 1, 1, and the others x x lambda 2 and 3 can be P2, P2 0, 1, 0, and the also X lambda 2 and 3 can be put as P3, yeah, P3 uh, minus 1, minus 1, 0, and 1. Hence, hence we have that P is equal to minus 2, 1, 1, and 0, 1, 0, and minus 1, 0, 1. This is our P. So, because of, yeah, so A can be diagonalized, yeah, diagonalized, yeah, because we have three independent factors. So A can be diagonalized. Okay, after we have A can be diagonalized. So what is the diagonal? Diagonal say that the eigenvalues uh, of A. Yeah. So this is will be what's what we have. Lambda one. Lambda one is one, and lambda 2 and 3 is 2. So this is 1, 0, 0, 0 to 2, and 0 to 0 to 0, and 0, 0, 2. Yeah, because this is must be lambda 1, and this will be lambda 2 and 3. Yeah. Okay, we have diagonal. Diagonal, just only putting the eigenvalues in the main diagonal. So now determine the PA. Uh, Sorry, this is something wrong, yeah. Yeah, should be it's not right, yeah. I declare you this is should be P D power of T and P inverse, yeah, like this. Okay, this is also should be uh, P D and P inverse. So hmm, sorry, sorry. I make a mistake in the formula, ya. P D P inverse. Okay, this is also P. This is will be P inverse. Okay, I have correct, yeah, correct the formula. So the correct formula can be applied to this problem. Number C, we must determine a power of 10. So C will be what is C? C will be uh, C will be A power of 10 is equal to P D power of 10 P inverse. Yeah. So P is have we have known minus 2, 0, minus 1, minus 1, 1, 1, 0. Then the third is 1, 1, 0, 1. And diagonal will be 1 power of 10, 0, 0, 0, 2 power of 10, 0, yeah, and 0, 0, 2 power of 10. And then this is multiplied by P inverse. Yeah. We can calculate P inverse by using symbolet. Yeah, you can uh, find the P inverse. P inverse. Yeah. This is minus 1, 1, 1, 0, 1, 0, 1, and this is 1 of power of 10, still 1, and 2 power of 10. What is 2 power of 10? 2 power of 10, uh, uh, 2 power of 4 is 16, 2 power of 8 is 8, 16, 16, 3, 9, 200, 5,
1024.
2000, 20,
1024.
1000, yeah, 1024, yeah. and this is 0, 1024, and yeah, still finding the p inverse. So this is a power of 10. Yeah, yeah, still finding p inverse of p, but it's shorter than multiply a 10 times. Yeah, a 10 times. Uh, and you can imagine that you must find a power of 1 million, maybe. Yeah, you must find a 1 million times. Yeah, but by using this formula, you just only calculate a p d 1,000 1 millions and p inverse. Yeah, it's still worth it. And then uh, you must know how to find the diagonalization. Diagonalization is a condition where you can find P and can find D from A. P is must be n independent factors, and if the p less than n factors, we say that A cannot be diagonalized. But if we find n independent eigenvectors, we say that A can be diagonalized. So we have this formula. Okay, Juan Lee and uh, Gilbert and also uh, Paulina Gilbert have left this meeting. Okay, I think it's the end of the materials of linear algebra for this semester. And if you have any problem when you do some exercise or some problem in this course, don't be hesitate to contact me and ask me how to solve or how to finish the problem. Okay, and don't forget to register yourself uh, next next day on Friday. I will open the present the presency the presency or the my ubaya for this course tomorrow, maybe 9:45. Yeah, you can register yourself in my ubaya to as a complement as uh, because you are joining this because you have joined this meeting. Yeah, you can register yourself tomorrow. Okay, John Lee, Paulina, thank you very much for your stay in this room, even you are in holiday. Thank you very much, and see you in the anytime, anywhere. Thank you very much, and bye bye. Good night.
Okay. Thank you, Mr.